Good morning, students. In this lecture we are going to discuss the fundamental theorem of homomorphism of semigroup, or it is also known as the fundamental homomorphism theorem. Okay, so first of all the statement: let f be a function from a S to T be a homomorphism of the semigroup S star onto the semigroup T star dash. Here we have two semigroup S star and T star dash, and F is a onto homomorphism from S to T. Okay, remember it. This is important thing. F is onto homomorphism from S to T. Now next is let R be the relation on S defined by A R B. A is related to B if and only if f of A is equal to f of B, where AB belongs to S. Then R is a congruence relation. First thing, R is congruence relation, and second is T star dash semigroup T star dash and the quotient semigroup S quotient R with binary operation ring star are isomorphic. Okay, that is T we can write as that is T is isomorphic to S quotient R. Okay, so what is the statement? Let us revise the statement. F is a onto homomorphism from semigroup S to T. Okay, then we have defined relation R as A is related to B if and only if f of A is equal to f of B. Then the theorem says that if this relation R is congruence relation and semigroup T star dash and the quotient semigroup S quotient R are isomorphic. Okay, this is the most IMP theorem of this unit 1. Okay, so please refer it as soon as possible. Okay, now first we prove that R is a congruence relation. To show, first of all we show that R is an equivalence relation. Okay, so first we prove that R is congruence relation on S star. For that, first we show that R is an equivalence relation. So first is the reflexive property. So A is related to A for every A belongs to S. This is clear because f of A is equal to f of A. This is always true. So A is related to A for every A belongs to S. Okay, because our relation, how our relation defined? Relation is defined as A is related to B if and only if f of A is equal to f of B. So f of A is equal to f of A. This is true for all A belongs to S. So A is related to A. This is clear. Now the symmetric property. A is related to B. This implies that f of A is equal to f of B. Or it is also can be written as f of B is equal to f of A. So we can say that B is related to A. So symmetric property is also satisfied. So R is symmetric, and third one is transitive property. A is related to B and B is related to C. What is A is related to B? We have considered A is related to B and B is related with C. This implies f of A is equal to f of B and f of B is equal to f of C. So this implies that f of A is equal to f of C. This is simple. Okay, so A is related to C. So R is transitive. Okay, so R is reflexive, symmetric and transitive. So R is an equivalence relation. Now next, the second property for the congruence relation. Let us see. Now suppose that A is related to A dash and B is related to B dash. Now we saw that A star B is related to A dash star B dash. Okay, so A is related to A dash. This implies that f of A is equal to f of A dash. Similarly, f of B is equal to f of B dash. This implies that f of A star dash is the binary operation for T. Okay, so f of A star dash f of B is equal to f of A dash star dash f of B dash. Now f is a homomorphism from semigroup S to T, which is onto. So this can be written as f of A star B from the homomorphism, because f is homomorphism. This can be written as f of A dash star B dash. Here not dash. Okay, This is binary operation for our semigroup S, and star dash is for semigroup T. So here we get only star, not star dash. Okay. So f of A star B is equal to f of A dash star B dash. That means A star B is related to A dash star B dash. So both the property for the congruence relation is satisfied. Okay, so R is a congruence relation on S star. Okay. Now, so what is the second part? What is our aim in second part? We want to show that semigroup T star dash is isomorphic to quotient semigroup S quotient R. Okay. So first of all we define a map. Let us define map F bar from S quotient R to T star dash. Okay, as follows. F bar of equivalence class of A is equal to F of A, because the element of S quotient R are the set of all equivalence classes of element of S. Okay, so we have considered equivalence class of A, and when we apply F bar on this element, then we get F of A. So first of all we saw that F bar is well defined. Okay, for that we have considered two arbitrary elements from S quotient R which are equal. Okay, so consider equivalence class of A and A dash are same, that is equivalence class of A is equal to equivalence class of A dash. Okay, now these two elements have the same equivalence classes. Okay, so these two elements are related with each other. Okay, so this implies that A is related to A dash. Okay, we have used this result many times. Now equivalence classes are same, so A is related to A dash. Now A is related to A dash, that means F of A is equal to F of A dash, because our relation defined in this way. A is related to A dash if and only F of A is equal to F of A dash. So this implies that F bar of equivalence class of A is equal to F bar of equivalence class of A dash. Okay, so we have considered two elements are same, then their images are also same, so our map F bar is well defined. Now we saw that F bar is 1 1, the reverse of well definedness. Okay, we have considered two images are same. F bar of equivalence class of A is equal to F bar of equivalence class of A dash. Two images are same. This implies that F of A is equal to F of A dash. Now F of A is equal to F of A dash, that means A is related to A dash. Now these two elements A and A dash are same, so equivalence class of A and A dash are also same. So whenever two images are same, then their elements are also same. So F bar is a 1 1 map. Now we saw that F bar is onto. So let arbitrary B belongs to T. Then there exists A belongs to S such that F of A is equal to B. Why? Because our map F is onto map. This is given in the hypothesis. Okay, this is given in our statement that F is onto homomorphism from S to T. So for element B belongs to T, we get A belongs to S such that F of A is equal to B. Okay, so F of A is equal to B, but F of A is equal to F bar of equivalence class of A. This is equal to B. Okay, hence for any element B belongs to T, we get equivalence class of A belongs to S quotient R. Okay, this element belongs to S quotient R such that F bar of A is equal to F bar of equivalence class of A is equal to B. So from this discussion we can say that F bar is onto map. Okay, what we have shown, F bar is well defined, F bar is 1 1, F bar is onto. Now only just one thing remaining, that is F bar is homomorphism. So consider two equivalence classes of A and B belongs to S quotient R. Now here we consider the binary operation for the quotient semigroup. Okay, So f bar of equivalence class of A ring star equivalence class of B is equal to f bar of, now ring star is defined as equivalence class of A star B. So f bar of equivalence class of A star B, this is equal to f of A star B. Now f is homomorphism f, so f of A star B is equal to f of A star dash, this is the binary operation for T, f of A star dash f of B. F of A can be written as f bar of equivalence class of A star dash f bar of equivalence class of B. So from this we can say that f bar is homomorphism. Hence f bar is homomorphism. Also f bar is 1 1 and on 2. Okay, f bar is homomorphism, also it is 1 1 and on 2. So f bar is an isomorphism. So S quotient R with binary operation ring star is isomorphic to T star dash. Okay. So this is the most IMP theorem of this unit 1. That is the fundamental homomorphism theorem, or we can say fundamental theorem of homomorphism of semigroup. Oh, now let us consider example related to this theorem. Okay. So example is, let A is equal to set of 0 and 1. Okay, set A contain two elements 0 and 1, and consider the free semigroup A star generated by A under the binary operation catenation. Now you now you know very well this. Okay, A star. So A star is a monoid with the empty sequence capital lambda as its identity. Okay. Free semigroup generated by A is a semigroup with binary operation catenation, as well as it is monoid with its identity is empty sequence capital lambda. Now let n is equal to n union 0, set of all natural number union 0, with the set of all non-negative integers. Okay, n is the set of all non-negative integers. Then n plus is semigroup, where plus is the ordinary addition. Okay, it is known n plus is semigroup. Then so that n plus is isomorphic to the quotient semigroup of A star. Okay, that is n is isomorphic to A star quotient R. Okay, so what is our aim? Our aim is to show that n is isomorphic to A star quotient R. For that we have to define one homomorphism, one relation R. Okay, one congruence relation R on set A star. So first of all we define. Now in this example we are using fundamental homomorphism theorem. So we have to define one homomorphism from our semigroup A star to n. Then after we have to define one congruence relation R on this semigroup A star. Okay. After this we says that this homomorphism is onto homomorphism. Okay. So let us see one equivalence relation. Sorry, not one relation which will be congruence relation. So let us see. Define function f from A star to n as follows. F of alpha is equal to the number of ones in alpha. What is alpha? Alpha is the element of A star. This is the finite sequence of elements of A, and the elements of A are 0 and 1. So alpha contains the finite symbols 0 and 1, and f of alpha defined as the number of ones in alpha. Now we have discussed this example in previous lecture. We have shown that f is a homomorphism as well as f is onto homomorphism. Then it is known that f is homomorphism as f of alpha catenation beta is f of alpha plus f of beta. Okay, we have considered the different cases for alpha and beta containing odd number of ones, even number of ones, and much more. Okay, so we have known that f is onto homomorphism. Also for 0 belongs to n, we get empty sequence belongs to A star, such that f of empty sequence is equal to 0. F of capital lambda is equal to 0 because the empty sequence contains 0 numbers of 1. Okay, so f of capital lambda is equal to 0, and for any arbitrary n belongs to n where n is non-zero, we get alpha containing n number of ones. Okay, we get alpha which is finite sequence of elements of A. Okay, and in this case alpha contains n number of ones. Okay, so the number of ones in alpha is equal to n. Okay, by this we can say that f of alpha is equal to n. Okay, so for any non-zero n we get alpha which has n number of ones such that f of alpha is equal to n. So f is onto. Okay, so here f is homomorphism, also f is onto. Now we define relation R on A star. How we can define? Let us see. Let R be the following relation on A star. Alpha is related to beta if and only if f of alpha is equal to f of beta. Okay, alpha is related to beta if we have defined relation R on the A star, because we are in this way. We define relation R on the star in this way because we are going to use fundamental homomorphism theorem. Okay, so alpha is related to beta if and only if f of alpha is equal to f of beta, because f is our onto homomorphism. So alpha is related to beta if and only if alpha and beta have the same number of ones. Okay, because f of alpha is the number of ones in alpha. So alpha is related to beta if and only if alpha and beta have the same number of ones. So by the fundamental theorem of homomorphism of semigroup, okay, what we have? We have defined one onto homomorphism from A star to n, and then after we defined one relation R on A star as A is related to B if and only if f of alpha is equal to f of beta. So this is the hypothesis of our theorem, which is the fundamental homomorphism theorem. Okay, so we get these two things. From these two things we apply fundamental theorem of homomorphism on this semigroup. So we can say that by the fundamental theorem of homomorphism of semigroup, R is congruence relation on A star with catenation. Okay, R is congruence relation on semigroup A star, and A star quotient R is isomorphic to n under the isomorphism. In our proof we have defined isomorphism as f bar is from A star quotient R to n defined by f bar of equivalence class of alpha is equal to f of alpha, where equivalence class of alpha belongs to A star quotient R. Okay, so here we have used the fundamental theorem of homomorphism in this example for the semigroup. Okay, what we have done? First we define homomorphism on from A star to n, which is onto. Okay, so this is the first statement of our theorem. Then after we define one relation R, okay, which is alpha is related to beta if and only if f of alpha is equal to f of beta. Okay, so we have derived two statement on semigroup A star and n. Okay, from this, then after we apply the fundamental homomorphism theorem. From this we can say that our relation R is equivalence congruence relation, and n is isomorphic to quotient semigroup of n star, that is n is isomorphic to quotient semigroup of A star. And from the proof we can say that our isomorphism map is f bar from A star quotient R to n, defined as f bar of equivalence class of alpha is equal to f of alpha. Okay, so this is enough for this lecture. We will continue in the next lecture. Thank you.